attempt to have you think about a different geometry. Let's simply push ahead and let's see how this might look. There's about a page or so of motivation of what this will look like in Sears, which I want you to read. So read the one-page motivation. And it's very analogous to a short motivation we had for Gauss's law by looking at a symmetrical spherical shell around a static charge. It's the same idea. But what we get out of this is Ampere's law. And so what it looks like is the following. Okay, so here's the sort of compare and contrast, which is a false one right now. What I mean by that will become more apparent in the next couple of weeks. Okay, so take a look at the newly introduced Ampere's law. So on the left side, we have an integral of some closed something. Something is now a line integral, let's say a loop, possibly a circle in this symmetrical case. So we're taking a line now, closed loop, and we're integrating along it. What we're integrating is whatever the magnetic field at every point along that line is, and we're doing the scalar product of that magnetic field with the length element of the ring. Okay? We integrate over the complete ring. On the right-hand side, it's proportional to the enclosed current. Of course, the Gauss's law for electric, static electrics, proportional to the net enclosed charge. There's a constant of proportionality, as with any magnetic phenomena. We are using permeability rather than permittivity. This is in vacuum in this case. And so in this sense, it looks very similar. We're relating the source to whatever it is that's produced by it, and we're doing an integral over the closed sum. Okay, so let's see what this might look like. Just sort of maybe a very conceptual example. Let's say I've got a current flowing into the plane of the board like this. We know already from our sort of right-hand rule use that the magnetic field associated with this circulates in concentric circles with the wire at its center. Hopefully I got this the right way around. Yep. And so this is the magnetic field associated with this. And what we're going to do is impose on this what becomes known as an Amperian loop. As with Gauss's law, it can be any closed shape whatsoever. So just to extremely sort of emphasize this, I could take some crazy kind of closed loop. Like this, and all I'm doing is everywhere along this closed loop, I'm looking at every point and figuring out what is the direction of ds relative to the magnetic field at that point, which is like so. I'll just call it b at that point, and I'm doing the scalar product of those two things and integrating it over the whole. Now, as with Gauss's law, if we're doing this for any reasonable situation, we would choose the shape of our Amperian loop carefully to benefit from symmetry of the situation. Okay? So if you remember what we did for Gauss's law, we usually set up our shapes so that the surface area element, dA, was either parallel or perpendicular to the electric field at that point. We're going to do something exactly analogous here. We're going to set up the shape of our Amperian loop so that it is either parallel or perpendicular to the B field everywhere, because that makes the scalar product either 1 or 0. So that's going to be our driving philosophy. So, yeah, question?
So do you just choose the direction of ds?
Okay, so now we have to talk about direction, right? Because there's some ambiguity here. So we need a convention. So the convention is so in terms terms of this, I guess I would say, if we are in the same hemisphere, if we're moving in the same hemisphere as the magnetic field, of course, then our scalar product is greater than 0. If we're moving against the direction of the magnetic field at that point, our scalar product is less than 0. Okay, so the usual behavior of the scalar product. What we need here is a convention for how we count either the direction that we're moving relative to the magnetic field, or analogously, how we say something about the direction of the enclosed current. So I'm going to focus on this for a moment and let me see if this makes sense. What we're going to do, take our curl of right-hand rule. If we are going around a Amperian loop, we wrap our right-hand curled fingers in the direction that we're traveling. And we're going to say that if the current enclosed within that loop is in the direction of our thumb, so following with this, I'm going counterclockwise around this green curve. If the enclosed current is in the direction of my thumb, we're going to call it a positive current. Okay? So I'll just write this down. Right-hand rule, wrapping around our chosen loop direction. So if the current is, let me say, in the direction of my thumb, positive. Is positive, and conversely, if it is in the opposite direction, so if it's in the opposite direction, then I is negative. Okay, I'm going to illustrate this in another way in just a moment. Okay, but let me just be clear what we're trying to do here. Indeed, we can go around these loops in whichever direction we want. There is some directionality now, unlike on the surface. So we have to choose a convention. I'm going to choose this one. Okay. So let me just do one other illustration of this, and then I'm going to pause for a question because I know some of you have that. Let me take the following as a slightly more developed example. Let me take now I1, which is here. Forget about those red lines associated with I1. Build up some complexity here. Let me say that I've got I2 coming towards us at this point. It's coming towards us. It's still within the loop. But let me take I3 out here, and maybe let me take, I don't know, I4 out here like this. Okay. So if I was to apply Ampere's law to this situation, what I would do is, first off, remember that I only care about net enclosed current. So remember, a lot of you are slightly, maybe mystified, is too strong a word, slightly curious about the fact that only enclosed charge feeds into Gauss's law. Here, only enclosed currents feed into Ampere's law. So it's easy to get confused by this, but any current that penetrates outside the loop, here or here, does not contribute when we're trying to figure out Ampere's law. So the first thing I would do is ignore 3 and 4 in this case. And then the second thing I would do is, let's say I'm choosing to go along this pathway in a counterclockwise direction. So I would need to do this. The complete integral of v dot ds as I go around this loop is, first off, mu naught, and then I need to figure out what my net enclosed current is. So by the convention I just outlined, I1 would come in with a negative current value. Why? Because if I'm going around this direction, my thumb is pointing towards us, this is going away from us, so in fact it would be minus I1. By contrast, I2 is coming towards us, and by this right-hand rule convention, I therefore assign it a positive value. Okay? So now we've arrived at the net enclosed current. Ignore 3 and 4, they're not within the loop. The sign convention we've just adopted, and that's all it is. It tells us that I2 should come in with a positive sign, and I1 should come in with a negative sign. All right, right, let me pause because there are at least a couple of tentative hand raises. Yeah.
So when you wrap your fingers, do you always go counterclockwise then? Or like,
No, I mean, I happen to go this way, but I can just as well go the other way, right? I mean,
will
I
that
can-
change your, whether you consider current positive or negative though?
Like, what's the convention for the chosen direction?
Whatever you want, doesn't matter.
But then positive and negative don't, because like, for instance, if I go this way, I'm gonna get like I can make my thumb point in or out, like it doesn't matter. So how do I know if it's positive or negative?
It's the same, right? I mean, it's the same thing you're doing, but your scalar product will have the opposite sign if you do that. So these will have the opposite sign, but so will your scalar product everywhere. Because you're going, locally, you're always going in the opposite direction here. So you get two sign changes, one on the left, one on the right, gives you the same answer, right? So if I'm going this way, what, in this case, let's look here again, the scalar product locally here is negative, because they're in opposite hemispheres. And I've just decided that I get plus I2 minus I1 if I'm going in this direction. But if I flip the sense, then here my scalar product is positive, because now this is in this direction, it's the same hemisphere as this. And these two flip sign. And that's true everywhere.
Oh, so the direction.
So I get a sign reversal on both sides that gives you the exact same expression.
Okay.
Yeah.
That's, current is following what?
Current is following the thumb.
Oh.
Yeah, I don't really know how better to say this. In this case, it's in the opposite direction. Yeah. Sure. So this is worth spending a bit of time on because we've got to get it down. So, okay, maybe I made this too complicated too quickly. First off, some random loop, this green thing on here. Forget about the red lines. That was just illustrative of the direction locally of the scalar product. Some random loop in green. I'm going to imagine walking around it in one sense, in one direction. As I do, I'm sensing the magnetic field everywhere. And I'm not only figuring out its magnitude in terms of the product here, but I'm also figuring out its relative direction to the way I'm moving. Okay, so that's the scalar part. So I'm doing that calculation, that measurement, if you will, everywhere as I go around here. But what I need is some convention, because I need a net enclosed current, I need a convention for deciding which of these is going to be positive and maybe which of them is going to be negative, depending on whether they're going this way or this way. So what I'm going to do is say I'm going to take my right hand, I'm going to curl my fingers, and that's going to be the kind of sense in which I'm moving around. If I have a current that is consistent with my right hand rule of thumb direction, I'm going to call it positive. So here I am coming around like this, counterclockwise direction. This one is coming towards me. So I'm going to label it as positive. It's going away from me, I'm going to call it negative. And it's just a convention, but I need a convention because these have directionality and I need the net value here. So I need to have a way of deciding which I'm going to call positive and which I'm going to call negative. Okay, Joseph.
For each B like component that you have a DS component, you're saying that the scalar product is the scalar product at each individual area, or what?
Correct.
Each individual current times what our scalar product with its the component of the E field that it's experiencing at that point, and we're just summing them all up at every single point along the.
Right. Right. So everywhere on this loop, I need to figure out what direction I'm moving, that's ds in green, and at what point is, at what direction and what magnitude is the magnetic field coming from.
So it's just a scalar line.
Well, it's a line integral of something that's a scalar product, yes. No.
Do we ever have to worry about the the actual direction of charge carriers? Like, don't we define the current by convention opposite of the direction?
Yeah, do not worry at all about the direction of negative charge current flow, charge carrier flow. Absolutely not. You've got to stick with one convention and stick with it, okay? So current for us is always only positive carrier flow, okay? Please don't go along that route. Okay, a little bit conceptual. Let's apply it to a couple of cases and see what it does for us. So we're going to start off with exactly the simple case I described, which is a straight current carrying wire. And as we did with Gauss's law, we're going to basically get a result we already knew. So a long straight conductor going to draw this coming towards us like so, and we are going to figure out the magnetic field at a point a distance r away. Okay, so we've done this by integration on Thursday. I'm not going to tell you what the answer is until we do it by Ampere's law. So how did we, with Gauss's law, based on symmetry considerations, how did we, for example, set up a Gaussian surface to figure out the electric field the distance r away from that charge? How did we set up our Gaussian surface when we were doing this? Yes?
Try to make the area vector parallel to the
Yep, so we want to rely on the symmetry and making the area vector parallel to the electric field. We'll do this. If we draw our surface at a fixed radius, we know the electric field is radially symmetric. So this gives us a symmetry that makes the integration for Gauss's law for electric field straightforward. Okay, so again, relying on symmetry, let's draw an Amperian loop a constant distance r away based on symmetry, and whoops, wrong place to draw, around the center. Smart. Draw it like this. Okay, that's supposed to be fixed r away. Okay, doesn't look like it, but it is. So this relies on symmetry. So the magnetic field everywhere along this Amperian loop should have the same magnitude since it's the same distance away. All right, for convenience, since we know something about the direction the magnetic field points around this circle, let's walk around it in that direction. So this is coming towards us. I know that the magnetic field is wrapping around in a counterclockwise direction. I'm simply going to start off and walk a full circumference around my circle and figure out what Ampere's law tells me. Okay, so obvious symmetry in this case. Okay, so left-hand side, again, similar thing we did with Gauss's law. Based on our choice of Amperian loop, we know that the magnetic field and the radial distance r away is constant everywhere around that loop. So I'm going to bring it outside of the integral. Scalar product we've already taken care of. In a sense, we've set ourselves up to walk around this loop in a counterclockwise direction. So the scalar product here always gives me what value as I walk around this in a counterclockwise direction. 1. Thank you, Hunter. Good. So we've taken this out. It's constant. The scalar product is an implicit unity, or 1 in here. It's plus 1 because I'm going around it in this direction. All I need to do is this. What's the total path length as I go around this Amperian loop before I get to little r? 5r. So we're done on the left-hand side. And on the right-hand side, okay, net enclosed current. Here's my right-hand rule convention. I'm going around in a counterclockwise direction. Does I come in with a plus or a minus sign? Good. Okay, everyone good with that? Joseph? looking everywhere, but what I care about is this direction relative to my local path walk, right? And I've chosen to walk around this in a way that I'm always in line with the magnetic field. So my scalar product, which is buried in here, is always 1. We'll talk about it after. Okay. All right, so now this tells me the result that you already know, and again, very much comparable to what we did with Gauss's law for complete closed Gaussian surfaces. I simply take this over here, and I figured out what the magnetic field is at that point. Okay? So this is the simplest case we can imagine. Let's take this a little bit more complicated, and as we did with Gauss's law for static charge distributions, let's take this and now ask the question, this is not just a point charge anymore, but maybe it is a large spherically symmetrical charge distribution, and maybe it carries, let's say, a total charge plus Q. And it's uniform, but I still want to find out the electric field, but now I'm trying to find out the electric field at a point inside that solid or continuous sphere. What did I do with Gauss's law for electrostatics in this case that would allow us to take this and now say that I'm looking not just at a current passing along a thin line, but I'm imagining a macroscopically large current carrying conductor. Say it's the radius big R, and it's carrying a total current unknown big I. What did we do here that will carry over into this case? So I know I'm pushing you a little bit on this. It's kind of reinforcing stuff from a month ago, but the ideas are so similar it's worthwhile. Yeah.
Can you think about a charge then?
Sure. And remember what we cared about in Gauss's law is the net enclosed charge. Okay? So if we're going to carry this idea somewhat over to this case, we'll do the analogous thing I care about now. And I want to find the magnetic field somewhere inside a macroscopically large current carrying wire.
Is everything inside still 0?
So remember, what I care about is the net enclosed current in this case. I wasn't going a little bit too fast here. Let's say the current is still coming towards me, but it's uniform. It's uniform. This is a cylindrical geometry. It's uniform everywhere within this circular cross-section. What I care about, if I'm trying to find the magnetic field at this point, is the net enclosed current within my my Amperian loop. So what do I need to do? I mentioned density. How do I translate this over into here? I'm just going to try this one more time, see if it works. So we went from a point charge, we drew a Gaussian surface, concentric spherical surface. Symmetry helps us. We figured out the net enclosed charge, did our Gaussian integral. When we expand this to be a macroscopically large charge distribution with the total charge Q uniform, what I did, trying to find the electric field somewhere inside this sphere now, is simply apply Gauss's law, but make sure I only worry about the net enclosed charge. And yes, we have to worry about the density. Yeah, go ahead.
Do you have to find like the relationship of the small r with I? So basically the
Right.
current at the small
All
r.
right, so let me paraphrase what you said. What I care about in this case is the fraction of the total charge that's enclosed within the Gaussian surface. In this case, I care about the fraction of the total current that is enclosed within the amp area. Let's just finish it off and then I'll stop. Questions? So, what do I care about? In this case, leave that up there because it's the same. So this is a uniform current. So the left-hand side of Ampere's law does not change. Again, I'm choosing this to reflect the symmetry. B at the distance r away is a constant. I'm going to bring it out of the Amperian loop. And I'm still going counterclockwise, and I know that the magnetic field is wrapping around in a counterclockwise direction. So the scalar product is an intrinsic unity or 1 here. And in fact, my path integral around a circle of radius r is still 2 pi r. So everything on the left side is exactly the same as it was. What differs is on the right side. And now the net enclosed current, well, let's say the total current was I, and it's uniform. So this is big R and this is little r. What's the fraction of the total current that is within my Amperian loop compared to the total current? Somewhere down here. Yeah, go ahead. Okay, small r squared over big R squared. That's true. Why? Well, the enclosed current I'm going to call little I guess, for now. I need to look at the ratio of areas. Again, it's uniform current. So I need the area of a small circle, cross-section, pi little r squared, divided by the area of the big circle, cross-section, pi big R squared. That is the fraction of the total current that is passing through my Amperian loop. So of course we drop the pi's, and I end up with this times big I in this case, and it's still in the positive direction, right? Because it's still coming towards us. So I've still got this here. So the only difference in this case is the fraction of the current that's within my Amperian. So what you get out of this, just rearranging it as we always do with these types of calculations, is that you pull together things that are constant within parentheses, something like that. That should be the big I in this case. Okay, so what we see is the magnetic field increases radially as I go from the center outwards. It reaches a maximal value at the surface, and then it drops off in the same sense we've seen previously, okay? So again, very comparable ideas to what we saw with the electric field inside a macroscopic spherical charge distribution. Increases linearly as we go outwards, and then it drops off with a 1 over r squared when we're outside. Yeah?
It makes a lot more sense to think of charge density, like as the charge spreading out over the volume, but I'm struggling to kind of think about current spreading out over an area, because current is, I'm thinking of current flowing through wires, so
Okay.
how do you,
So it depends what you mean by spreading out. I'm going a little bit more slowly than I wanted, but I'm hoping we might still have a chance to do this, and I think it's sort of what you're asking. The case I've just described is where I'm telling you that this is a constant current density. So I've just got a macroscopic cylindrical object, and the current passing along it has the same density everywhere, okay? So I'm taking this as a cylinder, the current density locally is the same everywhere. And so if I just take a certain small fractional area of this, the amount of current passing through it is that fractional value in proportion to the areas, okay? But there may be cases where it's not a uniform current density. And so this example up on the middle chalkboard behind me is one that is exactly that. It shows you that the current density varies with radial distance from the center. Again, it's still cylindrical geometry, but we're getting more current density as we go outwards. Okay? So complexity, it means we have to worry about that when we figure out what the net enclosed current is. And I'm going to hopefully have time just to quickly work through this, but I think that's what you're asking. What I don't want you to be thinking of is that there's any cases we'll be worrying about where it's not still a current flow that is along the axis. So it's always going to be current flow that is along that axial direction of the cylinder. We're not going to complicate our lives by allowing it to actually diverge or converge. It's always parallel to that axial direction. But it may be non-uniform. Okay. So let me just write up a few things about problem-solving strategy. I think I'm going to keep this up here. Okay. First off, it's always true, as Gauss's law, is, but it's useful in cases with useful symmetry. And again,